Whoops. Thanks, Gabe. Okay, so we have our length is 6 meters. Our height is 3 meters. Do we have our mechanical advantage? How many times less effort we have to put in by using an inclined plane? This is really easy, guys. It says it right here. Unless you can't read this. Can you read this? Yeah? Okay. Does someone want to tell me an answer? Sorry, that is divided by height. It's not very clear, is it? Anyone? Okay, so we have our inclined plane that is 6 meters long and 3 meters high. The length is 6 meters. The height is 3 meters. So the length divided by the height is 2. Does that make sense? 2. Okay. Easy. This is all. I guess it's hard to wrap your mind around what does IMA mean and which numbers do I plug in where. But we'll work through a couple of problems, and it turns out to be fairly simple once, but it does take a little time wrapping your mind around it. We'll skip those questions for now and move on to another plane. So the wedge, slightly different. It's very similar to the inclined plane, but it has a different use, and the mechanical advantage is to separate some heavy, to lift or split something. You know what a wedge is. But the important numbers are the length of the wedge, which is just a little bit different from our other definition, and the thickness of the wedge. So the ideal mechanical advantage equals the length divided by the thickness, which means if you increase the length, then you increase your mechanical advantage. So you make it easier to drive the wedge into the piece of wood or something. If you increase the thickness, you decrease your mechanical advantage, and you make it harder to knock into the wood. Gabe says, when you realize an ancient Viking was 10 times as smart as a modern scientist. That's an interesting observation. And not entirely wrong, but not entirely right either. The ancient Vikings, a lot of what they did was learning by example. And they saw something worked and something didn't work, but they didn't necessarily think about it as, the math. They didn't necessarily apply the math. They just said, okay, well, this works. Let's keep doing this, and they'll discover something else that works and keep doing that. Not that they didn't design things too, but it works. Yeah, we still do it today. That's a lot of engineering is just trial and error. And when it works, it's great. When it doesn't work, well, try something new, and maybe it works next time. And hopefully you learn something from your mistakes, and that's what it's all about. As a scientist, you try to figure out why, and why something works, and you might figure out what is the relationship. As an engineer or a scientist, you might try to figure out what's the relationship between the length of the wedge and the thickness of the wedge to how easy it is, which right now is is mechanical advantage. What's the advantage that you get based on the length of the thickness? And then you can teach someone else how to apply it exactly, and yeah, so we'll keep going. How about this one? A wedge is 30 centimeters long and 3 centimeters wide at one end. What is the ideal mechanical advantage? I'll go back. 30 centimeters long, 3 centimeters wide. Centimeters long, 3 centimeters thick. T. Jaden or Kayla, you can speak up too. It doesn't have to just be Gabe in the chat box. Good. Gabe's got it. Jaden or Kayla, does this make sense to you? Do you have a question that I might be able to help answer? It's hard for me to know whether you guys follow and understand me or not because I'm talking to my computer. So if I don't have your feedback, it's I just have to assume that you understand what I'm saying. So it helps me if you can, and would help you if you can ask me questions and that sort of thing. So if you don't have any questions, or you can ask me something like, hey, I don't understand what ideal mechanical advantage means, or how do you figure that, or something. Oh, it says I'm Josh Pearson again. Kind of lost. Okay, well, that's fine. That's not a problem. Let me let me speed ahead to some uses so you can see how the purpose, and then we'll get to okay, I thought there was a little more detail in here, but I guess there's not. Okay, so all right, so let's go back to, sorry, I'm trying to figure out how to explain this in a better way, because I must have missed, if you don't follow, then I must have missed something and not explained it well. So let's go back to understanding what a force is. Let's go, yeah, here. Okay. So if you can imagine that this force right here is someone, ignore the cosines and the theta and all of that. Just look at the force in the box. If you imagine that the box is glued to the floor, and that girl in that picture where she was pulling the door, imagine she's pulling on that box. So she has a string attached to the door handle, and the string is attached to the door handle, and she's pulling on the string. Even if it's not moving, she is exerting a force on, through the string on the door. If she's pulling at really hard, I don't know how many newtons that might be. Actually, I don't know how many newtons someone can pull. But let's say it's if you pull really hard, you can pull 100 newtons at 100 newtons. That's just a unit of force. So you're pulling 100 newtons and the door doesn't move, or the box doesn't move. So in a new scenario, imagine that the box is not glued to the floor. Well, the box is still going to try to resist your movement because it's going to be held back due to friction. So you can't just touch the box and it starts sliding. It's not on ice or anything. So you pull the force, and at some force you can move the box. And as soon as the box starts moving, say it goes distance d, you pull it. Gabe doesn't like that I'm using so many newtons. Anyways, okay, 10 newtons. You pull at 10 newtons of force, and you end up pulling, constantly. Force doesn't depend on time. You can pull, if you pull 10 newtons the whole way, all of that distance d, then you have pulled at 10 newtons, and your distance, let's say that is 3 meters. Then you would say work equals force, which we said was 10 newtons, times distance, 3 meters. And so your work would be 30, you can either call them Newton meters, or the metric unit is a joule, which is equal to a Newton times a meter. So what did we say? 10 times 3 equals 30 joules. And so you've done 30 joules of work. So now, say you want to say this distance d is not flat, but say you want to instead go up 3 meters. Well, you have to apply 30 joules of work to raise this box. Because we figured if you had to go, so you have to go 30 joules, exert 30 joules of work to pull the box up 3 meters, but that's not very easy because you aren't even 3 meters tall. So the purpose of learning these simple machines is joule. Jaden says joule is Joule for the scientist. So the purpose of these simple machines is to help you make it easier to move this box 30 meters into the air, or other types of things. So let's go down to here. So what might these simple machines do? Here's our simple machines. We've got a lever, a pulley, an inclined plane, a screw, and a wedge. So we said that simple machines make devices, help you perform work easier by accomplishing a couple of things. Option 1 is keep track of these. Options 1 through 4, you just know that I'm going 1, 2, 3, 4, and I'll ask you what they do. So you can transfer a force from one place to another, change the direction of the force from, say left to right, or up to down, or at some other angle. You can increase the magnitude of the force, or the distance, or the speed of the force. So what did Gabe say? Or you could be like 50% of America and pay the other 50% to do the work. Okay. Yes, you could pay someone else to do the work. Unfortunately, you are bound by the laws of physics, and you have to do some work. There's just no avoiding it. Okay, so let's take the first simple machine, an inclined plane. Let's take a more obvious one. Let's look at the lever. So, or it looks kind of like a seesaw. It's the same thing. Imagine there's a box on one side, and your sitting on the other side. So from the perspective, I mean, you're pushing down on the lever, and the box will then go up in the air. So what was accomplished using the lever? What simple machine was what did the simple machine do to make it easier to move the box up? Of these four options. Was it 1, 2, 3, or 4? You don't have to know. You can guess. Gabe says 1. Jaden or Kayla? Jaden says 2. Kayla says 1. Let's see. So when you push down on the lever, the box on the other side will go up in the air. So well, one thing we did was, number 1 is transfer a force from one place to another. Oh, okay. I made a mistake here. You're both right, actually. All three of you, I mean. Transferring a force from one place to another that's correct, because you pushed down on one side of the lever, and the resulting force was up on the other side of the lever. So that transferred the force from one place to another. But we also changed the direction of the force. As humans, it is often easier to push down because, that's in the direction of gravity, and we can, let our body weight pull us down, and we can do less work by just, giving in to gravity. That's easy. So our force is going down, and on the other side of the lever, the box is going up. So we also changed the direction of the force. So since I guess that was a trick question, it's actually 1 and 2. We did nothing to increase the magnitude of the force or the distance or the speed in this case, because the lever, well, it looks like the lever's in the middle. If we change the lengths and around, we'll see later that affects it too. But I guess often these simple machines may do more than one of these things. But let's look at. Okay, let's go back to our first example, the inclined plane. So you can imagine in your mind that you're in a wheelchair, or let's come up with a better example. You can imagine that this is a slippery ramp. Maybe it's wet with rain, or you pour some oil on it, and you're at the top of the inclined plane, and you have a big heavy box that you're pushing along, and then you push it down the plane. And rather than the alternative would be to instead of carrying it down the plane, maybe you're just carrying it down the plane. Instead of carrying it down the plane, you could jump and go down all at once. So the advantage that you get here is, rather than take a lot of force all at once, you jump down, maybe it's 3 meters, that's 9 feet, that's taller than you are. If you jump with a heavy box and you try to land, then that's really, really hard. Good luck staying on your feet. But on the other hand, if you change the distance, then you can walk down with this heavy box a lot easier. And so the engineering behind this simple machine is you make the distance that you travel longer, and the amount of work that you do, at least the amount of work that you do going just down, you can ignore the sideways direction. That is a different calculation. Just imagine just the downward part. The amount of work that you do down is the same, but since you increase the distance and force equals work equals force times distance, then your distance goes up, then that means, and your work is the same, your force has to go down. So you're taking less force, you're absorbing less force with every step downwards than you would if you just jumped all 9 feet in one big jump. Does that make the whole concept a little easier? Jaden and Kayla, how are you feeling about this? Is it still, am I still talking mumbo jumbo? Or is there something else that I can clarify? Kayla? So using an inclined plane is easier than jumping down. That's what you got out of it. That is up to you, I guess, and up to the simple machines when they're used in with an engineering mindset. If you can, it takes a little while to wrap your mind around how to use the simple machines effectively. But once you learn to take advantage of the simple machines, then you can find out how to make things easier. So maybe the inclined plane is the right choice to, if you have 9 feet to go and you want to jump down 9 feet, maybe let's make this a more, the number is bigger. Say you want to go down 500 feet. Well, you're not going to survive a fall jumping straight down off a cliff 500 feet. But if instead of walking, jumping down off the cliff with your box and then landing, if you instead take the long route down, then that's an effective use of the inclined plane, which is the slope of the mountain. You take the lower, the less steep route, and you might walk further. You might travel a further distance, but you make the amount of work. The amount of work just in the downward direction is the same, and that's often a key point because gravity is always fighting you. So, another alternative is, say you have a 500-foot cliff. What if instead someone engineers, some bright person, rather than carrying this box all the way down the mountain, what if someone decides to use another simple machine like the pulley? So they set up a pulley, they extend the pulley over the edge, and they tie it to a really strong tree, right? A couple of really strong trees. And so the pulley sticks out over the edge, and the rope goes all the way down 500 feet down to the ground. And, that's another way of accomplishing, you can tie the rope to the box and pull the rope, and if you put the pulley in the right spot, then you can pull sideways. It's like tug-of-war style. So this pulley is hanging over the edge, and you have a group of people all pulling, yes, sideways, like in the direction of the ground, not towards the ground. Like tug-of-war. And this box is moving up. So there's horizontally. Thanks, Jaden. That's what I meant to say. So if we look at what this pulley would accomplish, it is transferring a force. It's not transferring a force from one place to another. It's all along the rope, but it changes the direction of the force. So you get to pull horizontally, which is easy for you. It's a lot harder for you to pull up over the edge of a cliff. That's just, it's not easy. So you pull horizontally, which is, with a team of people, and the box moves up. So that, I think that illustrates, I hope that illustrates how these simple machines, if you were to use a pulley like this, and in our example, one of those ropes is horizontal, so you get to pull it all the way up the cliff, pulling horizontally, and the box goes up. So I think that hopefully illustrates how these simple machines involve a lot more of design rather than, a lot of times you could pick a couple of different simple machines, or you could put a couple of simple machines together to accomplish the job. But it's up to you to figure out what you think the best design is, and you can prototype it and put something out there, and then someone else might look at that and say, maybe if you put a lot of simple machines together, then you end up with things like trebuchets and that sort of thing. And that's what we're getting to. So, we're running a little out of time today, so, and we'll go into more detail on these specific simple machines. The other ones, we didn't really get into the screw. I talked about the pulley. I'll show you quickly. We can ignore the whole mechanical advantage thing. I think that's a little abstract anyways. Let's go to, I'll quickly cover the screw. The screw, the direction of force is a twist around, you're twisting a screwdriver, and the screw is moving into, you turn radially, and then the screw moves axially. Does that make sense? If you imagine a wheel attached to an axle, the screw moves in the direction of the direction that the axle is facing, and you're turning in the direction that the wheel would turn. So that's also changing the amount of, the direction of the force, and then depending on how many, you don't have to understand the math here, but depending on how many, how close or how far apart the ribs in the screw are, you can make it easier to go into a piece of wood, or more difficult by, making more, making you work by travel. If you go more distance, cover more distance turning, then it doesn't have to go in as far, and that's easier to do because you have to give less force per twist, but you have to do more twists. So that, then again, you see the relationship between if you might have to, if you are okay turning more further distance, then you can, and taking longer. If you have more distance, then you can exert less force for the same amount of work, which is what all of these simple machines do in some way or another. We'll skip we went over the lever. There's a couple of different types of levers. You can look into this more carefully if you want, but later. But or if we can go back over it later, I think we'll cover them later. But yeah, so this is the lever that we talked about. There's other types of levers. You can pull up, and more like a wheelbarrow. That's a type of lever. It uses other simple machines too, but the lever is by lifting, and you pick up something in the middle. Tweezers are another example of a lever. That's a little harder. It's even difficult for me to wrap my mind around when I first looked at it. So, but I don't know. You guys are good at Googling too. So if you want to look into these further, we'll skip this because I want to get on to give you at least a little bit of fun things to see. Let's see. And the wheel and axle. That's one last simple machine where you turn a big wheel and you rotate a very tiny, the axle is much tinier, and so for one big rotation that takes a lot more distance, you can, again, you turn a bigger distance, and the amount of force that you have to exert goes down to accomplish the same amount of work. Let's see. And we kind of covered the pulley. There's some pulleys get more complicated if you want to get more complicated with them. You can also reduce the amount of work if you start adding in extra strings of pulley. And for every string, you will briefly touch on mechanical advantage. For every string you add will increase the mechanical advantage, so it'll, say you add 2 strings, then you have to pull twice as far to move the same distance, but it's also twice as easy to pull. If you have 3 strings in the pulley or 4 strings in the pulley, it's 3 times as far, but 3 times easier, or 4 times as far, or 4 times easier. Okay. I'm sorry I'm running out of time on you guys, but I promise at the beginning of next class we'll cover some more of this. We'll quickly go over some cool ancient technologies. I know this wasn't the most exciting, but we really need to, it really helps to have some background on the types of different types of simple machines before we, that gives us some way to talk about these technologies. So one really cool ancient technology was Damascus steel. It's got this cool wavy pattern in the knife. It's super strong. It can even cut through inferior swords. Before, this is the strongest metal at the time. It kept an edge, and it was also flexible. That was really cool. The knives are like wedges because they are really thin, and they split things apart. That makes sense, right? So when you stab something with a knife, then you're taking advantage of the simple machine of the wedge. Roman cement and concrete. I guess not as much simple machine related, but very cool. It's only in the last 30 years that we were able to create cement and concrete as strong and as well as the Romans did. Once we started adding what's called fly ash to, they use volcanic ash, but it wasn't until 30 years ago that we built a dam that was actually theoretically as strong as what the Romans do. We don't know 100% sure because they did it 2,000 years ago and things degrade over time. But the Colosseum, while it's falling apart, is still standing, which is pretty amazing given that it's 2,000 years ago. Let's see. The ancient Greeks made napalm. Oh, yeah, one more thing. Romans also made cement that set in water. And people don't know how to do that nowadays. No one knows how they did it. It's a big mystery. It was lost in the Dark Ages. The technology was lost in the Dark Ages, and nobody knows how they did it. So everyone knows it's possible because they talked about doing it. They probably didn't lie about it. So that's an invention that a technology that we know exists, but we don't know how to do it. Gabe says, we build a house and it barely lasts 20 years. That's right, and part of that is we know that it's only going to last 20 years. The builders know, but they use cheap materials because people don't want to pay as much for a house. But that's true. We could certainly get a better investment out of our houses if we did more like the English do. In London, all of the houses, there's almost no new development. It's all redesigning the interior and that sort of thing. But the outsides are made of stone and concrete, and they last forever almost. It's very, very rare for them to have to. They just do maintenance work. So it's a difference in society. We tend to tear things down and build up new things. But I guess you can decide whether that's a good thing or a bad thing. So I'm gonna have to. The next group is coming on the same login as me, so I'm gonna have to get off a couple minutes early again. Hopefully, we'll get this issue sorted out. But well, we have a couple more technologies that we'll go through, and a couple of technologies that are that we can debunk that were not real technologies, and then we'll get into our next dive deeper into ancient engineering. I think we're doing either Archimedes, who did a lot more, who designed some really cool inventions with these simple machines, or siege machines. That's the next 2 weeks. I don't know which order they're going to be in, but thanks for showing up, and Archimedes screw, yep. Okay, see you later. And also, next time I'll get back to you. I said I would get back to you at something in the beginning, so I definitely have to go now, though, because the next class is starting. So talk to you next week. Let's see.